Today we're going to work with the sign test. It's difficult in the sense that it's very hard to explain exactly what we're doing. I have to show you what we're doing, and so that you get a feeling for how it's done without being told exactly what to do when. It's one of those things where you have to sort of understand it to do it. So I don't expect you to ever really have to do it, but I do expect you to understand it when someone else does it. And so we're gonna work through an example which will illustrate how it's done and maybe even why it's done. Let's start by saying not all data is normal. Now, we saw that last time. Not all data is normal. Take an example, questionnaire surveys. Now, frequently you get a questionnaire survey which says 1, disapprove, 5, approve, and then there's numbers between them. Supposedly 2 means mildly disapprove, and 4 means mildly approve, and 3, well, maybe it means neutral, but everybody who answers this has a different meaning to what those numbers mean. And the numbers themselves have no meaning. The only thing we can say about them is that they're ordered, and we call that an ordinal data. Ordinal because they're ordered. That is, the numbers, things go from disapprove towards approve. So if someone were to say 3, that means they approve more than they would have approved if they said 1. If they said 5, that's certainly more approval than 3. And 2 is less approval than 4. They're ordered. The order of the numbers is the order between the disapprove and approve. But the numbers themselves don't mean anything. And to think of adding them up and finding an average, which, by the way, is frequently done, really doesn't have a whole lot of meaning, because the number 3 is not necessarily in between 1 and 5. People might think that 2, 3, and 4, and 5 are real close to each other and sort of spread out their approval in here. Some other people might have 5 as total approval, but 1, 2, 3, and 4 might mean disapprove at different levels. So the meaning to these numbers don't have the same meaning from person to person, but they do have an order to them. And that's all we can say about them. Averages are not useful in a thing like this. However, they're often done. Now let's take another example, even more extreme. Say we're making a survey. What color is your favorite? We're gonna do a dance, and we want to decorate the room, and we make a survey. What colors would you like the room decorated? Brown, gray, or blue? Answer 1, 2, or 3. And we send out this survey, and 50% of the people said brown, and 50% of the people said blue. So we painted the room gray, because the average between 1 and 3 is 2. This, of course, is utterly meaningless. There's no average in this kind of data. These numbers are totally without significance. They are just labels. We're labeling so you can write the thing down on a abscan form or something, but there's no relation between the number and the color. Gray is not halfway between brown and blue. This is called nominal data. Nominal data is nothing but names. Nom, name. They're names, and the numbers are just names too, and they have no meaning whatsoever. To take an average of this is absolutely ridiculous. So when you have nominal data, you don't take averages. So what do you do when you have this kind of data? How can you make tests of hypotheses when you have this kind of data? And the answer is that you have to make what's called a nonparametric test. Nonparametric tests do not assume that the data is normal. That's the kind of test we need, a test that does not assume that the data is normal. The data can be anything. The data can be nominal. It can be ordinal. It's just not necessarily normal data. And we have tests that do not assume normality. We call them nonparametric tests. We're going to learn a couple of them this semester. This first one is called the sign test. So the example of a nonparametric test is the sign test. And now I'll give you the steps in doing the sign test. The procedure for doing the sign test is 1, force the data into a success-failure situation. And generally, it's called a plus-minus situation. That's why it's called a sign test. They don't say success, failure, true or false, heads or tails. They use plus, minus for the two categories, for the dichotomous categories, and then use the binomial distribution on it. Well, we know that if we have a dichotomous situation, we can use the binomial distribution and obtain probabilities. So what the sign test procedure does is force the situation into a simple situation with pluses and minuses, and then all you have to do is count how many successes you have, how many pluses out of how many trials, and then use the binomial distribution on it. Well, let's take an example. Let's say the administration gave a survey. It was going to do something, make some kind of change, and it wanted to see the students' approval. And 1 was disapprove, 5 was approve, and this is how the students rated things. 5 of them out of 20 students were surveyed. 5 of them highly disapproved. 9, I guess you'd call that moderate disapproval. 4, kind of neutral. 2, sort of approved. None of them really approved of it. Okay, this is the data, and the administration wants to test the hypothesis, their null hypothesis, that 50% of the students do not disapprove of the move. Okay, evidently they want to do this thing, and they want to justify it. So they're going to justify it by saying, I'm making a test of hypothesis that 50% of the students do not disapprove of this move, which means it's a good move. Right? So we got the situation, the null hypothesis, 50% of students, that is, pick any student at random, there's a 50% chance that he or she will not disapprove of the move. We're going to do it using the sign test. Since there are 20 trials, 20 students, each one who was asked whether they approved or disapproved, I will say a success, a plus, is a student choosing 3, 4, or 5. A plus, success, a plus, is 3, 4, and 5. That is neutral, mildly approve, strongly approve. We'll say that's a success because a student does not disapprove. If they're neutral or approve or mildly approve, they don't disapprove. Of course, if they give a 1 or a 2, then clearly they disapprove. So we'll exclude those. And 3, 4, or 5 will be do not disapprove. So now we have a situation, and of course the probability of that we're saying is 0.5. That's the null hypothesis, that it's 0.5. Is the data consistent with that hypothesis? Well, we observed 6 successes, 6 pluses. If you remember the data we had, there were 6 people who, out of 20, who said 3 and 4. None said 5, but 4 said 3, 2 said 4, and so 6 said 3, 4, or 5, so there were 6 pluses out of 20 trials. What is the probability that there will be, at most, 6 successes in 20 trials? This is the question we're asking. Because, why because? Why at most? Why are you saying at most 6? Why don't you just say, what's the probability of 6 successes, and show how unlikely 6 successes is? Why am I saying at most 6, no more than 6? Why? And that's going to take some explanation. Let's say I have a coin, and it's a fair coin, well balanced. And you were to flip it 1,000 times. And, well, what are you going to get? You'll get some number around 500. Not much chance you're going to get 500. The chances of getting exactly 500 are extremely small, like 0.001. But to get numbers near 500, like 475 to 525, add up all those numbers, that's pretty high. You're going to get a number pretty close to 500. Well, let's say you flipped the coin and you got 499. 499, and that's hardly evidence to say it's not a fair coin. I mean, if you flip 499 out of 1,000, clearly that sort of shows it's a fair coin, right? However, if I said, well, what are the chances of someone flipping it 499 heads out of 1,000 flips? The answer would be no chance at all. Chance is 0. Probability 0. I can reject the hypothesis any level you like because there's no real... Something occurred which really shouldn't occur. There's no chance. Something wrong here. Something's wrong. If statistics were to say, reject the hypothesis that it's a fair coin because you flipped 499 heads out of 1,000, something's wrong. Because 499 is a great number to flip out of 1,000. So is 498, 497, 501, 502. They're all great numbers to flip. However, the exact probability of flipping any one of those numbers is negligibly small. Now, let's say I have a coin that I suspect is unbalanced, and someone flips it 1,000 times and gets 400 heads out of 1,000. I say, gee, 400 heads, that's kind of small. I was expecting more like 450 to 550, not as low as 4. What are the chances of getting 400 heads? Well, that's not fair again. Because even if you flip 500 heads or 499 heads, the probability would be small. So there's no way I could make a reasonable test. However, what if I say, what are the chances of getting at most 400 heads? Well, at most 500 heads is a half. So that's not going to reject anything. At most 400 heads, no more than 4. He only flipped 400 heads, no more than 400 heads. What is the probability that someone will flip no more than 400 heads? It turns out that's extremely small. The chances of someone flipping no more than 400 heads with a fair coin is extremely small. The law of large numbers says, hey, it's going to be a lot closer to 500 than that. Okay? So we can reject if they only flipped 400, because the probability of 400 or less, no more than 400, is very, very small. That's the kind of test that's used in this kind of situation. And so that's why we ask the question, what is the probability that there would be at most 6 successes in 20 tries? That is, what is the probability of flipping no more than, or at most, 6 heads if this were a fair coin? This is a fair coin. What are the chances of flipping 6 heads? No more than 6 heads, or at most 6 heads. Well, let's investigate this at most business. Some people always have a little problem with at most and more than, so let's spend a couple of minutes on it. Let's talk about simply from the situation we had before. Remember these probabilities? I told you to remember them last semester, last lecture. So here they come back, just as an example. Let's say we're in this situation where n of 2 and p of 3/4. Here's the probability of no, 1, 2, 3. And someone says, what is the probability of at most 2 successes? Now, that's not this, or this. What at most 2 is the probability of none, 1, and 2. This is at most 2. At most 2 can be 2. At most 2 can be 1. At most 2 can be 0. 0, when I'm saying at most 2, that contains 0. 0 is in the set, in the event at most 2. 1 is in the event at most 2. 2 is in the event at most 2. And to get the probability of at most 2, then, I have to add up, because 1/64 of the time I'll win by having a 0, 9/64 of the time I'll have a 1, and 27/64 of the time I'll have a 2. The total is 37/64. So the probability of having at most 2 for this situation is 37/64. It's at most 2 is the same as 0, 1, and 2. Let's try another one. For the same situation, what is the probability of at least 2 successes? Someone said, what's the probability of at least 2 successes? And here is the original probability structure for n of 2 and p of 3/4. At least 2 is the same as 2 or 3. If I win, if I get at least 2, and I get 2, I'm going to win. If I win, if I get at least 2, and I get 3, I'm going to win again. Of course, I can only get 0, 1, 2, or 3, so I win when I get a 2 or a 3. And the probability of winning is the probability of the proportion of time I win is the proportion of time I got 2s and the proportion of time I got 3s. And that is 27/64 for the 2 and another 27/64 for the 3, or 54/64. I win at least 2, 54/64 of the time. Notice that at most 2 is the same as no more than 2. No more than 2 contains the same things that at most 2 contains. At Most 2, no more than 2. Notice that at least 2 contains the same things as no less than 2. If you think about it, they become obvious. But I've noticed people get them wrong all the time. So I'm pointing this out very carefully for you. Now, let's go back and answer the question. What is the probability that there would be at most 6? What are the chances of having only 6 successes in this experiment? At most 6 is 0, 1, 2, 3, 4, 5, 6. And I have to therefore find the probability of at most 6 in a binomial with n of 20 and p, okay, n is 20 and p is 0.5. That's the supposition. That's what they're saying. There's a 50% chance. And in order to do that, well, I'm not going to do it by hand. I'm going to go to the Minitab again and ask for the PDF of binomial 20, p of 0.5, and here are the numbers. Spitting them out. There are the numbers. Now I have to add up 0, 1, 2, 3, 4, 5, 6. If I add them up, I come to, looks to me to be a little bit less than 0.06. There's another way, a shorthand way of doing it. I can add those up, or I can, instead of asking for the PDF, I can ask Minitab to give me a CDF. Give me the CDF of 6, that is, CDF binomial 20, p of 0.5. The CDF is the probability that x is less than or equal to 6. Less than or equal to 6 is no more than 6. They mean the same thing. And it says k is 6, and the probability of no more than 6, or x is less than or equal to 6, no more than 6, is 0.577. 0.0577. Well, now, what does that tell us? If we make a test, and alpha is equal to 0.1, that is, make a 10% level test of the hypothesis that the administration, null hypothesis, that at least 50% of the student body does not disapprove of their move. At the 10% level, that's a weak test, 10% is higher than this. This, by the way, is the p-value. These probabilities that we're finding, they're the p-values. The probability of something happening is the probability value. That's what p stands for, probability. Okay, now we know what it stands for. And since this is bigger than that, we can reject. Since this is larger than that, we can reject the hypothesis that they are correct. And at the 10% level, we say, no, it is not true. However, what if someone said, make the alpha 0.05? It means I have to be 95% sure. I'm about 94% sure. I'm not 95% sure. At the 0.5 level, I must fail to reject. So at the 5% level, I must say, well, the administration could be right. Just about, just barely, but they could be right, and therefore I cannot reject the hypothesis that more than 50% of the students do not disapprove of the move. How about the alpha equal to 0.01? Well, at the 1% level, I have to be 99% sure. I'm only 94% sure. I'm not quite 99% sure. I must fail to reject. So at the 10% level, I can reject. At the 5% and 1% level, I must fail to reject the hypothesis. So the administration would probably come to us and say, I made a 5% level test of the hypothesis that 50% or more of the students do not disapprove of our move, and I accepted. That hypothesis was accepted by the statistical analysis. Accepted, remember? And they would therefore go ahead and do the move. What if they had said 40%? What if they backed off and said 40%? If they said 40% and I ran the same thing, the probability of being of less than or equal to 6 with 40% is 0.25. 0.25 I could reject. I would fail to reject at any level because 1 is not bigger than 2.5. 5 is not bigger than 3. There is no way I could reject this hypothesis. So if they said there's a 40% chance, I would have to go along and say, well, there's a good chance you may be right, and there's not much I can say It's possible that 40% of the student body does not disapprove. What if they really were foolish about this thing and try to say 60%? 60%. That the proportion of students, the probability of each student failing to disapprove is 60%. Well, the probability of having only 6 successes in a binomial situation, that is, binomial situation where the probability for each success is 0.6. I say, okay, what is the probability of having less than or equal to 6, no more than 6? Turns out to be 0.0065. And for the size of a test, 10%, the size of the test, 5%, the size of the test, 1%, all these are larger than that, and for all of them, I can reject. So, if they were to say that they're 60% of the student body, I would reject at any reasonable level and say, sorry, there's just no way we can accept that. But having chosen the 50% instead of the 60%, they can get away at the 5% level, not at the 10% level, but at the 5% level. They can get away with it. Okay, so we saw a use of the binomial distribution in the sign test, which is a non-parametric test. Now, admittedly, I do not really think that you could go out and solve a real problem using this material. However, you should have a feeling for it. So when someone else is doing it, you look over their shoulder and say, why'd you do this? Oh, yeah, that's the way to do it. And see whether they're doing something which makes sense or not. If they're doing something which doesn't make sense, I expect you to be able to catch them. But I really don't expect you to be able to do this all on your own, so don't fret if you cannot. Okay? Well, see you next time.